All right, well, welcome to 5.1, day 1 of chapter 5. And we are going to start right off and do some verifying identities. Now, mostly we're going to stick with the identities you already know, the Pythagorean identities, the reciprocal identities. We have a few new ones, but nothing too intense. But the main thing is that we're going to verify today. That's the biggie. Now, the only new identities we have today are the even and odd identities. And they are kind of referring back to even and odd functions and has to do with some symmetry. And rather than symmetry, though, I'm going to just think in terms of the unit circle and thinking about what's going to happen on a unit circle if you take the sine of an angle versus the sine of the opposite of that angle. For instance, if you're on the unit circle and think of yourself at a 30-degree angle, think about the sine of that angle versus the sine of a negative 30-degree angle. Well, the value is going to be the same. You're still up a half, but now you're down a half. So the sine of the opposite of your angle is simply going to give you the opposite sign of SIGN, the opposite sign of what you would get if you just took the sine of it. So in this case, I would be at a negative 1/2 instead of a positive 1/2. Okay, let's try again with cosine. What's going to happen on cosine at that 30? Well, think about what the cosine of a 30 is versus the cosine of a negative 30. Well, cosine is just how far over you are, and it doesn't matter if you are up 30 or down 30, you're still over the same amount. So when you take the cosine of the opposite of your angle, you actually get the exact same thing as if you just take the cosine of the regular angle. Okay, and then last thing, let's think about tangent. And tangent is basically, you got to look at the two scenarios I've already drawn. Do you think that the tangent at, well, I'll go ahead and draw it out. The tangent at 30, is that the same or is it the opposite of the tangent at negative 30? And it's the opposite. They are opposite signs in those two quadrants. So you would find the tangent of it and then just change the sign on it. All right, the reciprocal identities match the original. In other words, if you're doing cosecant, it'll be the opposite of the regular cosecant. If you're doing secant, it actually ends up being the same as the regular secant. And if you're doing tangent or cotangent, you change the sign on that one. Now, we're going to use these a little bit, not a ton, not near as much as we're going to use the others. So let's talk about what it means when we're saying, hey, we're going to verify identities. In all honesty, it's kind of like a proof. Remember geometry? Now, I'm not trying to scare you, but I know proofs in geometry weren't always everyone's favorite, but they're just a very systematic way of proving something is true. In geometry, you did these 2-column proofs. You'd have a statement and a reason. These are not really like this. These are more like algebraic proofs where you are showing step by step how something plays out. This is not something where you're wowing me with how much mental math you can do. It's a proof. So it's all about the work that you're showing me. I don't care what your final answer is. It's all about step by step. Can I agree and follow with your step by step proof? So an identity is a relation that's set equal. So you're going to have an equal sign. You're going to have 2 trig functions on either side. We're going to use our fundamental identities to verify more complex identities. So it's not going to say sine x equals sine x. It's going to be way fancier than that. But we're going to use those Pythagorean identities and quotient identities and stuff to reduce these down to where it does maybe say sine x equals sine x. And so to verify means prove that both sides of the equation truly are the same. So your proof is the solution. It has to be very explicit, showing step by step how to get each side of the equation to match. You're going to work with each side individually. You're not moving across that equal sign. You're not adding to both sides of the equation. Not that. You have to work individually on each side. I do have some hints as we do this. typically what we do is we work with the more complicated side first. Now that seems maybe backwards, but it's got more stuff that we can do to it to try to simplify it down to make it match the cleaner side. We're going to kind of do all that algebra stuff. We're going to look to factor or get common denominators to combine fractions. Another hint would be to look at what is in, like what's on the right side, what trig functions are on the right side, and you're trying to make the left side use those same functions. Now you will find that oftentimes you have just all kinds, you have 4 or 5 different functions going on. Maybe try to convert everything down to sines and cosines. But in general, you always got to try something. Don't raise your hand and say, I don't know even where to start. You've got to try something. You got to trade something out. Now, because what happens is these paths that maybe you try something and it seems to be going down a crazy path that doesn't lead you anywhere, that's going to give you insight and you learn from that. And it's actually kind of healthy and to struggle a little bit now, so that when you come across things on the test, you're like, oh yeah, that happened. I know how to fix that. So don't get frustrated. It's kind of actually fun. If you're into like solving puzzles or you're like systematic parts of algebra, step by step, this is going to be your gig right here. We're going to start with some easier ones and morph into some harder ones. Now, you really do need to know your identities well. It's another one of those things like the unit circle. If you don't spend the time to learn those identities and know them, then you're going to struggle through this because things aren't going to pop out at you. Okay, so when I'm looking at this, I have a secant, I have a cotangent, I have a cosecant, sorry, a secant, cotangent, and a cosecant. So that's a lot of different functions going. So I'm going to go with the path of turning things into sines and cosines. All I'm going to do is just start replacing. Secant x is the same as a 1 over cosine x. And this is just being multiplied. Cotangent, now I could write it 1 over tangent, but remember, I'm going sines and cosines. So cotangent is cosine x over sine x equals, and cosecant x is 1 over sine x. And now you're doing that algebra stuff. Like, oh, look, I'm multiplying fractions. I could reduce a cosine x with a cosine x. And I'm left at 1 over sine x equals 1 over sine x. We just verified it. Look, both sides are the same. That's our goal. Now, if I was just simplifying, I wouldn't want to leave that as a 1 over sine x. I would change those to cosecant x. However, that's not what I'm doing here. All I'm doing is verifying. I'm trying to get them to match. I don't care how nice they look as long as I can get them to match. Now, this is not the type of thing where you box in your final answer, because this is not what I am looking at. I am looking at all the work up here. So keep it nice and organized and clean so that I can follow it on your paper. I will give you 10 sheets of paper. It is not a competition to see who can use the most or the least amount of paper. It helps me if you don't write super tiny and I have to get out a magnifying glass to read it. It helps if you skip spaces between problems. All these things help me because I'm trying to decipher your work. And some of us, you know who you are, don't always make that easy on me. All right, so here is one where we might use reciprocal functions. These are just hints on this one. If you're going to use a reciprocal function, here's a quickie little shortcut. If you have a function in the denominator, like I have a secant in the denominator, that's a 1 over secant is really the same as just a cosine. So what I can do is I can just pop that up and call it cosine squared. If I have a cotangent in the denominator, I can just pop that up and call it tangent. And that's a nice way maybe to get rid of fractions if we don't want to have fractions without having to show me a whole bunch of work. That's the whole point of those reciprocals, is that if you just swap them, then they equal each other. Okay, now another hint on reciprocal functions. Remember that the whole thing with reciprocal functions is when you multiply them together, they just equal 1. So like a 3/4 times a 5/3. These are reciprocals. The 3's cancel, the 4's cancel. It all reduces to 1. So the same works in trig. If you multiply reciprocal functions, like for instance, if I take a secant x times a cosine x, that's just equal to 1. And so I could, if I see this, I could just replace that with a 1. Now you could show the work if it helps you, like you could change this to 1 over cosine x times a cosine x over 1 and show that those cancel, and now it's a 1. You can do that, but I'm allowing you this shortcut. And as you get better at this, you'll catch that more often. Early on, we might go ahead and do this until we get better and we start saying, oh, looky, that's going to get us a 1. And then we'll do this shortcut where we don't have to show that step. Okay. All right, let's practice another one. I got a hint here that we're going to be doing a common denominator, which seems weird because I don't have any fractions. But I also have an identity here I'm supposed to prove that has a sine, a tangent, a cosine, and a secant. All 4 of those are the same thing. Now, one of our hints was try to get this side to use the same trig functions on the other side, but it's only a secant. I'm not sure I could turn all of these into a secant. So I'm going back to my sines and cosines pattern. So I'm going to take this sine of x. I'm going to change it to this to sine x over cosine x. I'm kind of a fan of taking this and putting it over 1, so I catch that that's up on top. That's going to be on top when I have it as just alone and not a fraction. Cosine, okay, I'm going to leave it cosine, but I'm going to write it over 1. And then over here, I'm going to call this 1 over cosine x. All right, another thing, remember that cosine by itself doesn't mean anything. It's an operation, so you have to have the variable. Don't forget that x or the theta or the whatever variable they're choosing to use. You must have that with it. And sometimes we get in a hurry because our brain starts moving fast on us and we forget to put that x there. That is important. I take half-offs on that, so you don't want to do that. Now, my hint was that we're going to get a common denominator. So here I'm going to end up with a sine squared x over cosine x. I'm just merging those together because they're being multiplied. Plus, now here I have a cosine x over 1. I would like to get a common denominator, so I'm going to call it cosine x cosine x. Now that's going to be cosine squared x over cosine x equals, already got the common denominator over here. Now, normally when we do this algebraically, we kind of cancel out the cosine x. We aren't really doing that here. I say we're doing algebra, but we're trying to work separately on each side of the equal sign. So don't get sucked into doing things on both sides. Just work over here. I've got the common denominator. Let's merge it together as one big fraction. Cosine x. And then I have sine squared x plus cosine squared x. All right. Okay, I'm waiting for you to see something here. If you do not know your identities, you do not see this right here screaming at you. That is a Pythagorean identity right there. And that's why you have to know those identities so that you see, oh, look, that just equals 1. So I have 1 over cosine x equals 1 over cosine x. And we've got it. No need to box it in. This is what I'm looking at, all of it. Actually, on your homework, it will help me if you also include the given problem, because I'm giving you a worksheet, but I'm not giving you room to work on that worksheet. You'll do this on notebook paper. And if I don't see what the original problem is, that's hard for me to grade whether this stage is even correct. Now, I feel like I'm giving you a lot of rules here to follow. I'm not trying to confuse you or make this harder than it is. I'm just trying to giving you a heads up on the kinds of mistakes that are typical. Okay, so having just used that Pythagorean identity, I'm going back to, you got to know them inside and out. They're always squared. It never works unless they're squared, and there's always a 1 involved somehow. but it doesn't always have to look like this right here. Now that last one it was a sine squared x plus a cosine squared x. Notice I'm using theta here, and that's fine. It's just a variable. But sometimes what you'll see, instead of it written like that, you might see something like 1 minus sine squared theta. And because there's a squared term there and a 1, I'm immediately thinking, oh, maybe there's a Pythagorean identity here. And all this is the Pythagorean identity rearranged. It's the 1, and I've taken the sine squared to the other side. So this is actually the equivalent of cosine squared theta. So if I see this, I could replace it with just a cosine squared theta. It could work the other way too. Maybe it was a 1 minus cosine squared theta. Then I could just replace that with a sine squared theta. So again, if you see a squared with a 1, that's usually a hint you've got some sort of a Pythagorean identity going on. But you have to be careful that you watch the signs, because if I had something like 1 plus sine squared theta, then that is nothing. That is not something that I could replace because it's not supposed to be a plus sign. There's not an easy way to change that. So be careful of the signs. It does have to work perfectly. All right, this is my last one, and then I'm going to let you kind of work a little bit on your worksheet and your homework. So this one, my hint is try some factoring. Okay, so that might mean that you have a trinomial to factor. I don't. It's not a trinomial. Might be a difference of squares. It's not. It is a difference, but this is not a perfect square. What I do have, though, is a GCF that I could factor out. I have a cosine x in this term, and I have a cosine x in this term. So I am going to factor out the GCF. Let's factor out cosine x. What's going to be left in this first term is a 1 minus what's left in the next term is a sine squared x. And again, remember, you're just working on each side individually. Just leave this alone over here. I did, remember, work on the side that looks more messed up because I've got more things to do with that than what I can do with this over here. All right, let's ponder this a minute. Anything jump out at you? Okay, hopefully you recognize this from what I just got done talking about on the last slide. This is a Pythagorean identity that's been rearranged. A 1 minus sine squared x is really a cosine squared x. And a cosine x times a cosine squared x is a cosine cubed x. And I've matched them. So I just verified that identity. So this is an identity, this is an identity, this is an identity, this is an identity. Anytime you have two sides equal to each other, you're stating an identity. And what we're doing is just proving it. Now, I do want to talk a little bit. I feel like I'm going to get you to do this. And then I'm going to start getting some of you that want to go from here to here. And that's not allowed. It is a step-by-step process. You're making this replacement to this. You're not replacing this. You're at that point, you're doing too much in your head. And since it's a proof, it's got to be very explanatory of what you did from one step to the next. And I can't read your mind, so you can't go too many steps in your head where I'm having to kind of figure out what your thinking process was. All right, so again, keep your work super neat, write big, leave lines blank lines between problems. I would highly recommend not, like, if you skip a problem, give yourself plenty of space, because if you just think, oh, it's probably just a couple steps, well, if you can't figure it out, it might be a longer one. So give yourself room to do 5 or 6 steps, because if you don't leave yourself enough space, then you're ending up having to squeeze it in, and then I can't tell what's going on, and then I have to count it wrong. So here's what I've got. On your homework worksheet, we're doing 1 through 14. Now, it's longer than that. I think it goes, there's more problems than that, but we're just doing 1 through 14 because that's what I've talked about so far. And then tomorrow we'll do the rest of it. All right, jump in there. Good luck.